find the equation of a basic circle that has its centre at the origin, all we really need to do is draw one up and then label the radius as r, knowing that this radius then can move around anywhere on the circle. And if we define any point on the circle, let's call this one P for point, then we have to acknowledge that that point will have an x value and a y value. Now, what will that x and y value be? Well, it will vary as it goes around. When it's up here, the x and y will be positive. Over here, x will be negative, but y will be positive. Down here, they'll both be negative. And over here, the x value will be positive, but the y value will be negative. Well, that's all well and good. We can see that it can move around. And the x's and the y's are going to take different values everywhere it moves. But at any one place, we can always drop a line straight down and across and make a little right-angled triangle. Now, if this point is xy, that's because this distance here is x. Would you agree with that? And if this distance here is x, then we could label it as x. And if this other point here is y, that's because the height of it lines up with whatever y is at that point. So we could also define the height of this little triangle as y. Now, what would Pythagoras say about this right-angled triangle? He would say that x squared plus y squared equals r squared. Now, that is literally the equation of a circle that has its centre at the origin, where r is the radius. So this makes it really simple to define the equation of any circle then, because they all follow this basic rule. Now, we're talking here about circles that have their centre at the origin, so let's write that down. So where the centre equals 0, 0, and radius equals r. Okay, so if I ask you to graph, let's say x squared plus y squared equals 16, then we can see here that r squared is 16, so r must be 4. So very quick and easy to do. Draw up a circle, and our points out here are going to be 4, negative 4, 4, and negative 4. Now, obviously, every time you get a number here that is a perfect square, you'll have a number here that is an integer. But you could just as easily graph circles that don't have integers for their radius. For example, if we had x squared plus y squared equals 7, now that means that the radius must be the square root of 7. Because after all, if r squared is equal to 7, then r is the square root of 7. So to graph that one, you just write root 7, negative root 7, negative root 7, and root 7 all the way around here, and you're good to go. Now this holds true perfectly well, of course, when your x's or y's could be negative, whether one of them's negative or both, because when you square a negative number, you get the same answer anyway. So this relationship holds true all the way around the circle. The other thing you might be thinking of is, what about when we take the square root of something? I just said that if r squared is 7, then r is the square root of 7. Why did I not say it's plus or minus 7? Well, in this whole scenario here, we've defined r as being the radius, and so that's a length, and lengths have to be positive. So there's no need to write plus or minus 7 there. We know that the radius is root 7, and that means that when we go to make our distance from the origin of root 7, we'll naturally write positive numbers here and here, and negative numbers there and there. But the radius is still a length. This works the other way as well. If you're looking at a circle and you can see what the radius is, for this one we can see that r equals root 3, all you need to do is square both sides there, and you can see that r squared would be 3. So the formula for this circle would be x squared plus y squared equals 3.